All right, so we're talking about chapter 12, and specifically, so chapter 12 is entitled Memory Locations for Variables. And it's a funny thing, right? Because in the book that we've been kind of going through, the Weber book, Modern Programming Languages, we've spent a lot of time in that first, what is that, half the book-ish, a little less, talking about functional programming, in particular in ML. And one of the hallmarks of functional programming is that you don't think of memory, really. You're not supposed to. That's the whole idea. But in imperative languages, you do, and but we still have to turn our attention to it because if we're going to build compilers, we're going to implement languages, we have to have some sense of what's going on in terms of memory, and that's what this chapter is all about. And we'll talk about functional languages and also just other kinds of languages and how these things are kind of dealt with. We'll kind of break it down. The first kind of point here, before we even get to the table of contents of this whole kind of set of lecture podcasts that deal with memory locations for variables, is this notion. We've talked a lot about binding, right? The notion that there are values that get bound to variables, right, at various times and in various ways. We've talked about a lot of those kinds of things, right? Well, obviously those values have to go somewhere. They have to be in memory. And so therefore the variables have to somehow be bound to memory locations, back to this, this concept of binding. The burning question is, how do you do that? And it turns out to be, as always, not super simple. There are some straightforward concepts, and then a whole bunch of subtlety. And as you can probably imagine, everything in the world has been tried at least once, and we're going to try to hit the most prevalent and sort of relevant kinds of things. And the first thing that we just kind of want to talk about, and I alluded to it at the very beginning, is that there's kind of a difference between how functional programming conceptualizes this versus imperative programming. In imperative programming, the concept of a memory location, it's how you teach programming, right? There's a spot in memory, we'll call it A, it's going to get a value called 0, and we're going to do stuff there, and we can change it, we can combine it with stuff, and there's side effects, and it's just part and parcel. Even in languages like classic languages like Pascal, where you didn't necessarily have to think of it, in contrast to, say, C, where pointers become very relevant, and pointers are simply address locations, right? Even then, the notion of that variable is the name of a location in memory, that's always kind of how that's taught. In functional languages, it has to be like that also, but you don't talk about it. It's like it's hidden. It's like a family secret. Nobody talks about it. And one of those things you cannot talk about at Thanksgiving dinner. But the truth is there are memory locations in functional programming languages, but again, so you say val A gets 0, you're going to bind A to the value 0, but in both cases there has to be memory, right? And therefore they both face the same question of how do you bind that variable name, that label, right, that symbol, if you will, to a specific location in memory in order to work, in order to do what you do. So this is kind of the table of contents of where we're going to go. And there's a lot of different ways of looking at this, and we're going to specifically talk a lot about activation records. And as you can kind of see, we're going to break a lot of this down relative to activation records. And we'll talk about nesting functions and functions as parameters, some things like how do you deal with that when you're moving all that stuff around. But we're going to start with the notion of function activations. So the concept here, I don't know if I like the name, if I like the term activation, frankly, but that's the term. And an activation is what the slide says: the lifetime of one execution of a function from call to corresponding return. That's an activation. So put another way, it's the time period in which the function is alive, right? A function comes alive, whether you've instantiated an object or whether you've made a call into the function, right? And this idea that functions get called and stuff gets shoved on the stack, and broadly, about that kinds of idea. What we're going to do here is break that down a lot more in much greater detail as to what's going on. What's going on there is an activation, okay, for that function, and then some kind of activation specific information that allows us to hang on to all that stuff when the function comes alive, and then clean it up when the function goes away. And if you're wondering, is this what garbage collection is all about? Yes, indeed. This is one of the things that garbage collection is all about. So just remember, though, that an activation, it's a funky term. I apologize for it. I don't know what I would call it instead, but that's the term. When you've got a variable and it is bound in some way to an activation, what that means is there's a variable bound to that function coming alive, and there's a variable, and it goes away, and the variable goes away. That is called an activation specific variable, sometimes called dynamic variable or an automatic variable, and that's in contrast to a static variable, which we're going to talk about. And some of you, that have done C++ are like, whoa, wait, is that what static is all about? Yes, that is what static is all about. And so this notion that there are variables that sort of exist within a context of an activation, meaning, again, when a function comes alive, okay, and whose lifespan, kind of goes away when the function goes away. And immediately what some of that is, local variables, data that's inside of an object that we do anew, and we create the object, right, from some, definition, from some class. Well, there's a point when it comes alive, and then space is allocated, and constructors get called, and, and it's going to go away, and destructors are called, and stuff like that. That's kind of the idea. So let's start with ML, okay? Just an ML example, and we did this one earlier in the lectures, right? And so, the activation specific variables are the most common. They're the easiest to think about, right? Function comes alive. There's local context for certain things. We create some space while the function's alive. Function goes away. We tear the space down. This one where we have a function, and you may remember this one, where I think we introduced let via this function, where we say let these, and these become local variables, right? Well, while this thing is running, those variables get allocated as space, as memory. Then we perform the operation. That function goes away. The context is gone. The activation ends. And the memory is freed up, okay? So they live during that time period. There's also this notion of block activations, and I need to say that block activations are very particular to languages and to implementations, okay? Some languages, for example, here's again some ML, right? Some languages are going to say, all right, I've got a function called fact. I got a parameter coming in. I'm gonna allocate some space. I'm gonna shove that. I'm gonna make this comparison with the value there. I'm gonna have b. I've got val b, right? And I'm gonna allocate that. And some languages are gonna say, as soon as this function is activated, I'm gonna allocate n, and I'm gonna allocate b, and we're gonna use them. Well, it turns out that doesn't always happen that way. For example, a language might choose, where it's doing dynamic allocation like ML, it might come in and say, well, I know I need n because the value's got to come in, and then so I get n. But if that guy's true, then I go to, this thing evaluates to 1. I never get to the else, right? The else falls on through. So why allocate b? Well, if I don't need it. Well, in that kind of a context, then this value b lives within a block. And we call that an activation, okay, a block activation, where b lives only while the block that contains b, in other words, this else clause, when that else clause is executed, then b comes alive. And when the else clause is done, B goes away. And if the else clause never runs, again, interpreted language, right? If the else clause never runs, then B is never allocated, right? Because there was never an activation of that block. I hope that makes sense. I think that's reasonably clear. There's also, just other notions of lifetimes, okay, for variables. Again, commonly you think of, oh, I made a function call. Function is called, it gets created, we allocate some space for it, right, on the stack, typically, unless it's part of an object that's getting new and then it's being created somewhere. But that's kind of the common way, but it doesn't have to happen that way, okay? Most imperative languages, there's a way to create a variable so that it occupies a single memory location and exists forever in runtime. The earliest, imperative languages that I used, like Pascal, it was not uncommon to do sort of like central coordination between different, uh, maybe I want to say threads. These systems weren't always multi-threaded. But even if they weren't multi-threaded, there was still a sort of a communication between chunks of the code, or maybe you built a state machine, which is like roll your own multi-threaded, if you want to think of it that way, right? And I would use a global variable. You would set this variable, and when the program showed up, that global variable would be allocated and initialized. And then, of course, where this goes is, race conditions and, serious errors and stuff by misuse of global variables. But global variables did have a place as kind of a common semaphore or a common repository. And the point being here that the lifetime of a global variable is the life of the whole program, okay? So in this case down here, this is C. I declare this int count, right? And he's outside of any context, so he's a global variable. And we can view it as a static variable if we want, but he's a global variable for sure. And then we can use him here, and we can use him anywhere, So notice that he's out there, and then, inside this context of next count, he's used. Somebody else later on can also talk about count, do something with count, and it's going to mess with the very same variable out there that everybody else is. Again, it's not generally considered great style, these days for a whole bunch of reasons. Certainly not in the object-oriented world where information hiding and encapsulation was such a big motivation, right? But I think you get the idea, right? That this notion of global variables and things that live for the entire runtime of the program. And then it's possible for the lifetime and the scope. That global variable, it was called global because the scope was global. And it so happened that the lifetime was also matched up and aligned with the lifetime of the program itself. Well, you can also, in modern languages, by using certain features of the language, here's C again, you can do things that will actually cause a difference in the scope and the lifetime. And again, remember, the lifetime has to do with when is the variable created and when is it, torn down. When is space allocated? When is that space deallocated so it can be used somewhere else? That's what lifetime's about. Scope has to do with where you can see it, right? Global variables, everybody can see it. Unless you define a local variable of the same name, everybody gets to see that global variable. Well, here's an example of that same function, next count, only I've declared a static int called count. Now, what's interesting is his scope. Everybody outside this function cannot see count. Inside the function, they can see it. They can return it. Of course, outside of that, it's not going to be called count. I mean, it could be, but it doesn't have to be. So the scope is right here and very, very constrained, but static says, I'm going to set him up and he's going to have a lifetime that's going to persist for the whole program. I want that space for a number of reasons. That is why that's allowed in the language. I want that thing to have a lifetime that's sort of global, but the scope is not global. The scope is local. Now we talk about, I mentioned kind of earlier object-oriented languages, and typically in object-oriented languages, the lifetime of a variable is associated with the object lifetime. That ought to be pretty straightforward and obvious, right? And that you allocate an object. I mean, the whole idea behind object-oriented programming is the encapsulation of data and methods. So the object is created, the data is created. We have constructors that allow us to initialize that data and set things up, and destructors that tear things down. But that's pretty common, right? There are also languages, so that's the object-oriented approach. There are other languages that have variables that actually last across multiple executions of the program. That's a very interesting idea. I haven't personally programmed in a language that does that. I don't even know off the top of my head which programming languages does that or do that. But in any case, we're kind of focusing in this series of podcasts in chapter 12 on the activation specific variables. Okay, the kinds of variables that are spaces allocated when when the function is called. That's really what we're talking about. So we have to talk about this notion of an activation record, and again, it ought to be pretty straightforward. Activation, again, is when a function comes alive. So an activation record is just a data structure, so that when that function comes alive, the data structure is initialized. We got the variables that are allocated. We run the constructor if there's such a thing in that language, which allows us to initialize stuff or whatever. But we create this activation record with everything else the function needs to sort of live its life, okay? The return address, where it's got to go back to when it's done, all those kinds of stuff, okay? So yeah, down here, the activation record has all the variables, the return address, and a link to the caller's activation record, okay? A link backwards to that activation record. And we're going to get to that, about why that becomes an important thing, because it turns out that because of scoping and things, we don't always find what we're looking for right in our own activation record, because something is contextually outside of us and we've got to go out there to get it, okay? And then, we talked about this notion of block activation, right? Where, say, in an interpreted language where a certain chunk of code, if that code never runs, then the block is never activated. If the code is run, the block is activated. So in that kind of a situation, then there's a block activation record, okay? Which is an activation record specifically for that block of code, all right? And when we enter it, we got to get some space, right? So this just kind of points out, a number of ways of doing that. One of them that we could do is and I talked about this earlier when we introduced this notion, that you could just put all the block stuff, in the function's activation record, right? Either, and you could do it a number of ways. You can allocate space for a block activation record in its entirety, or you could take all the stuff that's in the block and just allocate those variables. And essentially, what you're doing is you're kind of just subsuming the concept of a block in that instance, okay? Another approach is to take the function's activation record, and then, if you think of it in a stack, then when you enter a block, you grow it, you extend it, right? And then when you exit that block, you shrink it. You kind of like push the block's activation record on the stack, and you pop that activation record back off, right? So that's kind of an example of that. And then the other one is that you just allocate different block activation records, as needed, and then just keep track of what's being pushed and what's being popped. So what we're going to do for the rest of this sequence, this is kind of where we're going next with this static allocation. We're gonna stay in the domain of activation specific variables, and specifically about activation records, and then look at all the nuance of kind of how we deal with that.